Good day, Mathalino. Again, I am Junvert. In this video, we are going to discuss the best solution for propped-cantilever beam. Okay, so when we say best, we are actually talking about subjective condition, which means that it will vary from person to person, and it will vary also with the problem at hand, depending on who you are, depending on what your skill is, your skill sets, and also the problem that you are that you are going to solve. For simplicity reason, we have here the propped cantilever beam. When we say propped cantilever beam, that is actually a cantilever beam with simple support at supposed to be the free end. But this is a first degree indeterminate structure. So this becomes indeterminate because of this additional support at the free end. Now, we have this very simple load located at the center, concentrated load located at the center of the midspan of our beam. So how to solve this one? I will present to you different solutions to solve this problem. Number one, of course, by direct formula. This is very convenient if you are allowed to open notes if you are in practice. So there's no problem with opening the notes. But if you are preparing for the for an examination, most of the time you are not allowed to open notes. So which means that this solution required that you memorize formulas, or if not, and hopefully it is given in your exam the formula to be used. Okay, so the formula, we are going actually to solve three problems or three reactions for this problem. The reaction at the simple support, okay, the reaction at the fixed support, and the moment reaction at the fixed support. The value of R1 actually is this one, 5/16 of P. That's it. That's the answer. The reason, because we have this direct formula. The R2 actually is, of course, 11/16 of P, because the total R1 plus R2 is equal to P, the summation of forces vertical. And the M2 is actually equal to -3/16 of PL. Okay, that is the answers. Sir, do I need to memorize these three formulas? No need. If you are familiar with the cantilever beam, if you have one formula only, you can find the other two. Let us say that you already know the R1, this 5/16 of P. No need to memorize the R2 and the M2, because we can find this R2 by summation of forces vertical equal to 0. Summation of forces vertical equal to 0. We have this R1 plus R2 is equal to downward P. Of course, we already have the value of R1. We can solve for R2. That will become P minus R2. What is the value of P minus R1? And we have the value of R1, P minus 5/16 of P. Of course, 1 minus 5/16, that will be 11/16. And that is the value of R2, even without you memorizing this formula. How about M2? If you did not memorize the value of M2, but you memorized the value of R1. So, of course, M2 is the summation of moments, all moments at point 2. Summation of moments at 2. What are the moments at 2? Number 1 is this R1. The length of this span is L. The moment arm is L. The force is R1. Excuse me. Minus this P. It will rotate counterclockwise, or it will bend the beam downward. We have this P. The moment arm is L/2. That's it. Substitute the R1. We have this L times R1, which is 5/16 of P minus PL/2. Okay, so we have this 5/16 minus 1/2. That will result to -3/16 of P times L. We have this P times L, P times L. So 5/16 minus 1/2 is -3/16, and this is our answer, PL. That's from the formula also. All right? No need the disadvantage of this formula, if the case will go in different ways. Let's say the load is not really exactly at the center of the span. Let us say it is located 2/3 or 1/4 or wherever that is not at the center of the span. This formula is no longer applicable. Or in most cases, there are distributed load in between. So, which means that this formula is very specific for a very specific condition only. That's the disadvantage of this formula. And for the advantage of this formula, very rapid if we memorize this formula. Okay? The advantage of this approach. That's it for the direct formula. Another is superposition method. Sometimes we call this the method of consistent deformation. What we are going to do if we don't have the direct formula, whatever is available for us, we can use that. Let's say that we memorize the formulas for the cantilever beam because that is a basic formulas for the determinate structures. So let us select which of these three unknowns we are going to solve first. Are we going to solve first the R1, the R2, or the M2? If you decide that you are going to solve the M2, then this structure will reduce to simply supported beam. Okay? Simply supported beam with M2 as your load. Okay? Take note that M2 now is not a reaction but a load. And also this P, this is also a load. Okay? The original load and this unknown reaction, you convert that into load. Then you are going to solve the value of M2 using the elastic curve of the beam, okay, of the simply supported beam. But I will suggest for this cantilever beam with prop support at the fixed end or at the free end, you are going to convert this into cantilever beam only. Okay? Which means we are going to solve first the R1. Let us solve for the R1. Let me erase the writings. In that way, we are going to separate. That's why we call this the superposition method, because we are going to separate the loads. We're going to separate the P and the load R1. So let us start with the P, that is the load P in the cantilever beam, and this is the load R1. Take note that for this method, this R1 is no longer a reaction but a load in the cantilever beam. Okay? Now, we are going to use the deflection. This R1 will cause this beam to deflect upward because this is a push upward. And we have this delta 2, we call that delta 2. And the value of delta 2 actually is, if you have this formula, that is equal to PL cube all over 3EI. You can find this formula in our website at node 1096. You can go to mathalino.com/node/1096 and you can find this formula. We can actually flash that in your screen. Where is that browser? We have this. The method of superposition, we have this list of formulas here. This is the formula we are going to use. The PL cube all over 3EI, the maximum deflection of the cantilever beam at the free end with load at the free end. We need also this formula, the slope at the end of the cantilever beam. Okay? The theta PL squared all over 2EI for the delta 1 what we are going to solve. All right, let's go back to the PowerPoint. We have this delta, that is for delta 2. And we also need this formula for angle theta at the free end, that is equal to PL squared all over 2EI as I mentioned earlier. Now, we are going to use this theta to solve for the deflection deflection due to this load P. Now, due to this load P, this half of the beam, L over 2 in length, will bend in that way. Okay? But this other half, from this point up to the free end, is a straight line. Okay? Because there is no load between this point and this point, so this will be in a straight line. And this is our total deflection. We call that deflection at 1. This total deflection is composed of two items. Number 1 is this value. Okay? This deflection here, may I choose a color? This deflection from this point up to that point. What is that deflection? Only That is the case of a cantilever beam with concentrated load at the end, which means the formula we're going to use is this one. So the delta 1 therefore is equal to, okay, due to this condition, this is length is L over 2, but here we have this L, so our equation will become P times L over 2 cube all over 3EI. That's it. Plus this portion here, we already solved this deflection from this point up to this point. We also need to express this deflection. What is the value of this one? That composed of total delta 1. What is the value of this portion here? Let us call this y. Tangent of theta. And the theta actually, if we are going to create a tangent line at this point, because this is a straight line, it will just prolong the line. Okay? And this is our theta from the horizontal. That is our theta. We call that theta 1. And take note, from the horizontal to the line, that is the theta 1. That is also theta 1, this portion here. Tangent of theta is equal actually to opposite, or theta 1. Where is that pen? We have this theta 1 is equal to opposite y all over the adjacent L over 2. Therefore, the y is equal to 1/2 L tangent of theta 1. But take note, in deflection, tangent of theta is actually congruent to theta because these values of theta are very small. The slope here are very small, so the tangent of theta is congruent to theta. In general, if we are talking about deflections or slope of the beam, the theta is congruent to tangent of theta. So therefore, our value of y is actually 1/2. We are going to write it here. 1/2 L theta. So this will become L over 2. Okay, L over 2. Theta. Our theta is PL. Okay. Our theta is this one. For the half, we are going to use L over 2 in here. PL over 2 raised to 2 all over 2EI. That's it. That is for 1/2 L theta. Our theta is this formula. This formula in here. That is the delta 1. And we are going to equate that with delta 2. So, the delta 2 is simply the force, our force here is R1 L cube all over 3EI. In the actual beam, in our prop beam, there is actually no deflection at this point 1, at this point at the prop end. So, which means that the total deflection here is 0. When we write the total equation, delta 1 minus delta 2 is 0 because that is as support. So we have this delta 1, which is equal to PL cube. I change the color, PL cube. All over, we have this 8 times 3, 24 EI. Okay, plus, we're still at delta 1. PL squared times L, that is also PL cube. We have this 4, 2 squared is 4 divided by 4. This is 1/4 divided by 4, that will become 1 over 16 EI minus delta 2, which is R1 L cube all over 3 EI is equal to 0. Cancel EI. Cancel L cube. Then we can solve for R1 because 1 over 24, let us go to our calculator, the Casio calculator. Let us calculate that value. Okay. Change position here. We have this 1 over 24 plus 1 over 16. Okay. 1 over 16. What happened? 1 over 24. Scroll. Plus 1 over 16. That is actually 5 over 48. So we have this R1. Change color. R1 all over, no, yellow. R1 all over 3 EI. No more EI. R1 over 3 is equal to 5 over 48 of P. Solve for R1. And this is our answer. Okay? The R1 is 3 over 48. Actually is 1 over 16. That will become 5 over 16 of P. And this is our answer. That confirms from our formula in the first solution. In our first solution, we have this 5 over 16 of P. Alright? That is our answer. Next. The double integration method. Do you like the double integration method? So we have this. The first thing to do in double integration method is to position your XY plane. So you are going to orient your XY plane. The suggestion is put that at the right end, the rightmost support. So we have this support here. So that will serve as our origin. And we're going to cut this second segment. We have these two segments, L over 2 and L over 2. So we're going to cut this segment. Distance X from the origin. Okay? And we're going to consider the all forces to the left of this section. Okay? So sum up all moments to the left of this section. We are going to write the moment here. The concept for the double integration method is this one. The EIY double prime is actually the sum of moments at this point or at that section. What is the moment at this section? Number one, we have this R1 times X minus P. The moment arm for P is this distance. This is actually X minus L over 2. So this will become X minus L over 2. That is our equation for the double integration method. Now we are going to integrate this twice to find the deflection. So first integration, we will arrive with the equation of the slope. EI y prime. That is the equation of the slope. This is only power formula. So this will become 1/2 R1 X squared. Minus, this is also power formula. So this will become 1/2 of P X minus L over 2 raised to 2 plus the constant of integration C1. Integrate it again for the second time. We get this equation of the deflection, EIY. So this is also again a power formula. So this will become raised to 3 all over 3. We have 1/2 divided by 3. That will become 1/6 R1 X cubed. Minus, this will become raised to 3 all over 3, also 1/6 of P X minus L over 2, okay, raised to 3, plus C1X plus C2. That is the double integration method. Now, to solve for the equations of slope and deflection, we are going to apply the boundary conditions. So for boundary conditions, this one, boundary conditions. Condition, which point? Conditions. Which point on the beam we know about, we know something about the deflection or the slope. We know about the slope or we know about the deflection. Of course, we know the deflection at the left support because this is a support. There is no deflection here. The deflection here is 0, which means that at X is equal to 0, or at the origin, the deflection is 0. Okay? So what is the value of C2? We can actually find the value of C2 here because this is 0. X is 0. This is also 0. anything inside this angled bracket that is negative will not be considered in the equation. So 0 minus L over 2 is negative L over 2. So we're not going to include this in our calculation. So this is 0, this is 0, this is 0. This is not included in the calculation. For the reason why, you can watch our another video about the double integration method, why we are not going to consider any value inside the angled bracket if it will become negative value. Okay? So therefore, if this is 0, this is 0, this is 0, and this is not included, therefore the C2 is 0. So we have this value for C2. C2. The C2 is 0. Another condition at X is equal to L. There are two conditions at X is equal to L. Number one, the deflection is also 0 because we have fixed support here. And therefore, the deflection there is 0. Okay? So at X is equal to L, the value of Y is 0. This is 0. It's equal to R1 L cube all over 6 minus, we have this L1 minus 1 half is 1 half. Our X is L. From here, our X is L. So L minus L halves is L over 2 also. Raised to 3, that will become L over 8. 6 times 8 is 48. Am I correct? We have this PL cube all over 48. Okay? Plus C1 times L. We already know that C2 is 0. Do not write that one. So we have this equation for C1. The C1 is equal to transpose this PL cube all over 48. That will become positive. So we have this divided by L. PL is squared over 48. We have this R1. So minus R1. L is squared all over 6. This is the equation for C1. Another equation for C1 is when at X is equal to L, when we apply this boundary condition, the value of the slope there is 0 because the tangent to the elastic curve at this point is actually horizontal. So the Y prime there is 0 at that point. Okay? That is another boundary condition. As remove my camera feed. Okay? So at X is equal to 0, at X is equal to L, the Y prime is 0. So we are going to use this formula, this equation, to write another equation for C1. This is 0. 0 is equal to 1 half R1 L squared all over 2. Okay? R1 L squared all over 2 minus, this is L minus L over 2 is also L over 2 raised to 2. That will become L over 4 times 1 half. That will become L over 8. Okay? PL is squared all over 8. PL is squared all over 8 plus C1. So we have another equation for C1. C1 is equal to, or we can actually substitute this value to here. So we have this R1 or 0 R1 L squared all over 4 all over 2 minus PL squared all over 8 plus C1. Our C1 is this line. PL squared all over 48. This is the value of C1 minus R1 L squared all over 6. Now we can solve now for the value of R1. Yeah, we have this 1 half minus 1/6. I need a calculator for that. 1 half minus 1/6. Calculator. 0.5 minus 1 over 6. 1 over 6. That is actually 1/3. So we have this R1 L squared all over 3. We can actually cancel out L squared. We'll do that later on. We have this negative 1/8 transpose that will become positive 1/8. Positive 1 over 48 transpose that will become negative 1 over 48, which means that we are going to calculate this value. We have this 1/8 minus 1 over 48 of PL squared. That is 5 over 48. 5 PL squared all over 48. Alright. Cancel out L squared. Then we have this value of R1 times 3 both sides of the equation. This is our answer. Actually, 5 over 48 times 3. Let's do that in our calculator. Times 3, that is also 5 over 16. So we have this answer, 5 over 16 of P. And this is our answer. Confirms that we are also correct based on our previous solution. Alright? That is by double integration method. How about the another method? We have this area moment method. Personally, this is my favorite solution. Especially if the loadings are more complicated, I will always run to this type of approach, to this approach actually. If you ask me what is my favorite approach, my answer is always biased to this in favor of this approach, the area moment method. Now, for the area moment method, we're going to solve for R1 also. Let us draw the moment diagram by parts with the fixed support as the moment center. So, for the R1, this is the moment diagram for the R1. Okay? For the P, the moment diagram is P times L over 2. That is also a straight line. The magnitude is R1 times L. And the magnitude of this P is, because this is downward, that is P times L over 2. That will become negative PL over 2. Now, let us call this point 1 and point 2. If you are going to draw the elastic curve, this is the approximate elastic curve. And if you are going to draw a tangent line to this at this point, okay, at point 2, because this point, the tangent here cannot rotate, we will have a horizontal tangent line. Okay? So, how to use this diagram? From this figure, the elastic curve and this tangent line, the vertical distance of this elastic curve and the tangent line is 0 at point 1. We call that vertical distance actually the deviation. The deviation of point 1 from the tangent line through 2, 0. And we have a formula for this deviation. Area of the moment diagram by parts between 1 and 2 times barred x from 1. This is equal to 0. That is our formula. So we have this area of this triangle. Take note that our barred x is measured from point 1. So we have this area is 1/2. The base is L. The altitude is R1L. Okay? Barred x from point 1. Let's rewrite that. Okay? Barred x from point 1 actually is 2/3 of L. It will become 2/3 of L. That is our moment arm or centroidal distance of that area from point 1. How about this area here? This is small area, small triangle, we have this minus, that is negative area. 1/2 base is L over 2. Altitude is PL over 2. Okay? The distance from this point, the centroid, up to this point is how much? In terms of L. Of course, we know that this is 1/3 of L. Ay. Boom. This is 1/3 of L over 2. 1/3 of L over 2 actually is L over 6. So this is L over 6, which means that this is L minus L over 6 is actually 5 over 6 of L. So the moment, the centroidal distance is 5L all over 6. Okay, this is equal to 0. That's it. We can now solve for R1. We have 1/2, cancel 2. We have R1 L cube all over 3 minus, we have this PL cube, PL cube times 5. 5 PL cube all over 6 times 8 is also 48. is equal to 0. Or we can transpose that one. That will become positive. So cancel out L cube. We have this value of R1. Again, 5 over 48 is 3 over 5 over 48 times 3 is 5 over 16 of P. We have already the value of R1. And if we have the R1, we can easily solve for the R2 and the moment at 2. That's the solution, the area moment method. Another solution for this problem is the conjugate beam method. I am not fan of this one. Okay, I don't know, but because I think because of the effort behind the conjugate beam method, because you are going to draw the moment diagram by parts like the area moment method, then after that you are going to draw the conjugate beam. For the conjugate beam, the length of the conjugate beam is the same as the original beam. So if we have the length L, the conjugate is also of length L. The roller support in the real beam, also roller support in the conjugate beam. Okay? Now for the fixed end of the real beam, that will become a free end in the conjugate beam. Okay? This is now our conjugate beam. Now we are going to load this conjugate beam with the M over EI diagram. So whatever is the moment diagram by parts, that will be the load of this conjugate beam. So we are going to load that with our diagram. That is our loadings. The magnitude is the same with these loads. R1 times L and PL over 2 downward because that is negative. Okay? Now, to solve this conjugate beam, we're going to find the moment here. We know that the moment here is 0. Even without applying the concept of the conjugate beam, we can solve for R1 because our task is only to solve for the R1 or for the reaction. So we have this summation from the conjugate beam, summation of moment at, let us call this point 1. Okay? Moment at 1 equal to 0 in the conjugate beam. That will become 1/2. Actually, this is the solution we wrote in the area moment method. Base is L, R1, the altitude is R1 times L. The moment arm is this one. Okay, this is 1/3 of L. L over 3 or 2/3 of L. 2L over 3. Okay? Minus this rotation here. We know that this distance is 5 over 6 of L. So 1/2. Base is L over 2. Altitude is PL over 2. Moment arm is 5L over 6. This is equal to 0. Alright? So, we have this R1 L cube all over 3 is equal to transpose. We have this 5 PL cube. 8 times 6 is 48 again. So, cancel out L cube. Again, we have the same answer. For R1, that will become 5 all over 16 of P. This is the answer. Okay? For the conjugate beam method. Another solution for this problem is the 3-moment equation. How to solve this by 3-moment equation. Okay? For the 3-moment equation, for the fixed end, we are going to extend, we are going to create an imaginary span. Let's call this 3 points, 1, 2, 3. Okay? Now, let us write the 3-moment equation. The 3-moment equation is this one. Moment at 1, length 1, 2, plus 2, moment at 2, length 1, 2, plus length 2, 3, plus moment at 3, length 2, 3, plus factors, the 3-moment equation factors, 6a barred a all over L for span 1 to 2, plus 6a barred b all over L for this span 3 to 2 is equal to 0. That is our equation. So that is the 3-moment equation for span 1, 2, 3. Now let us write the elements in our equation. Number 1 is the moment at 1. Of course, that is 0 because that is a simple end. 2 moment at 2. Length 1, 2 is actually L. Length 2, 3 because this is an imaginary, any all values in the imaginary span are 0. So 0 plus moment at 3, imaginary also 0, plus factor. This is actually 3/8 of PL squared. If you don't know where this value came from, you can actually check the 3-moment equation factors. Let us flash our browser. And I check if I flash already the browser. Okay. For the 3-moment equation factor, we have this value here at the center. The load at the center, this is 3/8 PL squared. 3/8 PL squared for 6A barred B and 6A barred A. You can find this value at this link. Okay. matalino.com/node/1707. Okay. 3/8 PL squared. We are not going to discuss thoroughly each method here because we are just comparing different methods in solving this problem. Three-eighth of PL squared. 3/2 is imaginary, so this is 0, is equal to 0. Now we can have the value of M2. This is the difference now with respect to other solutions, because this solution, we started with solving the moment instead of the reaction. The moment reaction instead of the vertical reactions. M2L is equal to negative 3/8 of PL squared. Cancel out the 1 of the L. Cancel this one. Cancel that one. So we have this value of M2 negative 3 all over 16 of PL. And this is our answer for M2. Okay? The same answer in our direct formula. Negative 3, 16 over. And if we have the value of M2, we can solve for the R1. Okay? We have the value of M2 already. We can solve for the R1. May I go back to the solution? By summation of forces or summation of moment at 2 is equal to negative na to. Of course, it's not 0. 3 over 16 PL. Okay? So summation of moment at 2, we will have this R1. We have this R1 here. Upward, R1. R1 times L minus P, which is downward, L over 2. It's equal to negative 3 all over 16 of PL. Again, cancel out L. Cancel out L, cancel out L, cancel out L. We have this P over 2 transpose that will become positive 3 over 1/2 of P minus 3 over 16 of P. That will give us the value of R1, which is, let's do the calculator. To make it sure, we have this 1/2 minus 3 over 16. Okay, that will be 5 over 16 of P. 5 over 16 of P. That is our answer. Okay? How about you? What is your favorite solution for this problem? What is your favorite approach for this type of problem? The propped-cantilever beam. Okay? Just comment below if you have that. This is not exhausted list now of approach. There are many other solutions that I didn't mention in this video. You can have what we call this, the energy method, the Castellanos theorem, and many more. Okay, I will not enumerate them all. I cannot enumerate them all. Okay, so just comment below what is your favorite solution for this type of problem. Thank you for watching. I hope you learned something. Have a good day. See you in our next upload of video. Bye-bye.